All right. Hi, everyone. Thank you for coming. Josh, can you hit record? All right. For the sake of the video, this is San Francisco MySQL meetup. Tonight we have Ori and Ari from Akabon. They're going to give a talk about some of the technology they're using in the MySQL world. Our sponsors, as usual, we have IGN, facilities, My Time, food, beverages sometimes, Percona, they provide food, beverages, speakers, books, that kind of stuff. And O'Reilly Media, they generally provide a bunch of books, but I've been really bad about ordering them. So we don't have any books to raffle off this month. But I promise I'm going to order those before the next time. We have next month, I can't remember the exact date, but we're going to hopefully have Twitter coming in talking about their systems. So that should be pretty interesting. As one of the sponsors, you know, IGN is hiring. Basically, all of our sponsors are hiring. It's kind of the thing. DBAs are in demand. So if you're a DBA and interested in working for one of our sponsors, check them out. And hopefully they'll keep giving us free stuff if they hire somebody one of these days. There's been hires. It's just, it's always looking. Aaron, am I missing anything? All right. Oh, yeah. Oracle is actually a sponsor. They're giving away a pass to MySQL Connect. I can't, at the end of the month. So, and with that, that's all I really have to say. So I'm going to go ahead and turn it over to Ori here first and go from there.
Hey. So I'm Ori, or maybe Ari. It's hard to tell. Thanks for coming. Any developers? There's a few. DBAs? Even less. Okay. Welcome, everybody. I want to start it off just giving you a sense. I know Ari has been here before, but I just had to have the stage for 5 minutes of glory, and then I'll be out of here. Has anybody seen a Keyban before? Well, that's cool. Yes, you have. Okay, test coming up. To give you a quick sense, we're developing a new class of database, which is not SQL or NoSQL. What it does is it's completely oblivious to the type of data that you want to put in it. So you can put tabular data, you can put SQL data, you can put JSON or XML, geospatial, any data that you'd like into one holistic data structure. The nice thing about it is you can also access it in exactly the same ways. So if it's SQL or if it's JSON, the data is available for you in any format. What I'll do in a second is give you a sense of where this actually comes from, and then Ari will take you through some of the things we're trying to solve. But to start with a little bit of my own background, I was the DBA developer kind of person who got both. And I kept hitting the relational database because it looked something like this. Familiar? Anybody want to guess what this schema is? It's nothing you would know, just trying to see. I had a lot of these, and they weren't like this. They were 10 times this, a lot of tables in them, a lot of data in those tables, and it just drove us crazy. So we realized at some point that there's something missing, there's something that doesn't work. And what we realized is that when we build applications, we build them with objects, right? Developers build with objects, right? Developers here. You're maybe in Java or in Ruby or whatever it is that you use, and you know what you're trying to capture. So maybe it's users or customers or patients or products or whatever you're trying to capture. The problem is you have those objects, you try to put them in a database, and what happens? It explodes, right? You get 100 tables for this stupid user object. Why the heck do I get 100 tables? And what is going to happen next, which we all kind of know. So anybody using ORMs in the room? Like Rails, Hibernate, that's all? Really? So that's kind of the classic. Here's Mr. RM, here's my object, put it in the database, and oops, it just exploded. So the understanding was, I have objects. They're in this database somewhere, but they explode into all these different tables. And what I wanted is a way to keep the flexibility that SQL gives me and the ability to query, but not suffer anymore. So the core idea is table groups. What you see here is the same schema as before. These are the same tables, but they're organized in some way. And what we're really doing is we're taking tables that belong together and explicitly say that. So for example, this is the users table, and they have a bunch of information about them, like qualifications and memberships and tags about them and capabilities and feedbacks they got and languages and so on and so forth, right? So it starts making sense. So it's really nice because you can look at it and kind of get a sense of what this company is actually doing. They have users on one end, they have jobs that they track on the other hand, and they try to match, you know, the right user or user jobs, right? So it kind of starts making more sense. So that's kind of nice, but the real magic isn't at how we visually lay it out. It's under the hood where we realize that we shouldn't store tables at all anymore. And that's the core, the source of when I say it's a new class of database, it's not a tabular relational database. We don't store tables anymore. What we do is we'll take the related information. So for example, a user with all of his related information, so with his memberships and qualifications and tags, etc., and co-locate those rows, put them together. Really what I'm doing is I'm interleaving them, right? I'm building a document or an object from the related data. So think about it for a second. I had in my application, I had this object. It translated to all these tables, but really under the hood, it stays together. So it has several really nice properties. If you think about this user that has all this related information, it kind of keeps that data together. So what we did is, instead of having a logical and a physical model that is tabular, we said, yeah, we can keep the logical model as tables, and in a second you'll see as JSON or anything else that you want to have. But under the hood, there's one holistic physical model that supports all of those. The way it's actually done is, the way this interleaving is actually done is, if we start with 3 tables, say I have users and orders and items, the classic, I'm sure you've never seen this schema before. And in a relational system, the users will go to one table, right? And the orders will go to a different table. And the items will go to a third table. What happens for us is we keep the logical view the same, but we realize that we can co-locate this data. So we logically keep it the same. Physically, I have documents that I can work with. So I can retrieve one of these documents in a single request. I can put it in a single request, right? Doesn't matter how complex it is. I can access it through JSON if I wanted to, and it's in one place. But I can also run queries. So each one of those rows remains an independent row. So I can run a query. The only difference is if I have a join between users and orders, or between orders and items and other kind of joins. Those joins are free to execute, right? They're already present in the data structure. I don't have to go and now execute them. So not only can you actually access objects and persist objects, you can actually run queries on top of this, and you don't pay for all these joins. So extend this a little further to the schema that we saw before, and suddenly you have, instead of 25 tables and all the joins between them, I have 2 table groups. And the most that I'll ever join is one join between those table groups. All the other joins are contained within the object, right? So our mission is to not join the SQL or no SQL movement. Our mission is to solve problems. So whatever your data is, if it comes from XML or JSON or any kind of stream or from tables, they can sit holistically together and you can access them using any one of those mechanisms.
So it appears as a denormalized database from the outside, and internally you may or may not do any normalization optimization. It's transparent.
I think yes. Let me say it in my words that yes, and because you're exactly right. So if you think about it, if I go to the schema that you saw before, it's almost as if I denormalized these two, but I didn't, right? that's what you said. The magic of it for me is that we keep the schema operationally active, right? It's every row exists exactly one.
Functionally, you're denormalized, but in practice, you're normal.
Right. So where I do denormalize is I take away the cost of those joins. Where I don't denormalize is I don't have any redundancy, as opposed to real denormalization. Precisely, yes. Exactly. But you can write the same SQL as before and everything as before. So that was 20 seconds of the life of Ori in the past 5 years. Thank you very much. I'm out of here. No, yeah, actually I am. Any questions for me? Who is she? Is she allowed in here? Yeah, go ahead. Schema changes. Never heard of it. We actually made it a lot easier to change your schema. I'll give you a quick answer, and later on you can nail me down to get the code, and you'll see how it works. Let me start with the easy part. Say you wanted to access this as JSON, which you can. And you wanted to put JSON, which you can, and suddenly your JSON started evolving. What actually happened? The schema just evolved, right? So think about the ways that it can evolve. Suddenly, instead of this user having just these properties, there's also phone numbers, right, which don't appear here. So what are we going to do? We designed the system to mostly do metadata changes rather than physical changes to the data. We'll just add a table, a level here, right? It's called phones. And that's done in a sub-millisecond response time. It doesn't lock anything. It doesn't change anything. And I know exactly where you're coming from. MySQL is DDL hell, right? I've been there. So there's no such hell. The same for adding a column. You don't have to lock the whole table and say, OK, nobody move for the next 5 hours until I add this column to the table. It's a metadata change. So it's a logical change, right? And we're working towards making all of these operations, and I think that will be finished in the next, I'm looking at my product manager, in the next couple of months. But what that means is that even if you try to drop a column, for example, we don't have to right now drop all of that data. We need to drop the definition of the column so you don't see it anymore, and make sure that the data evaporates over time. So the idea is that the schema can and needs to evolve over time. This is exactly what I was looking for when I was looking at the new SQL solutions, but I was missing the other part, being able to actually get some information out of that database. The other question or the other part of the question is actually a more interesting one. We're working with several gaming companies, and that's actually very interesting because just like you said, they have no choice. I'll actually, I don't know if I have. You have? I'll give you a sense. So think about, while I'm looking for it, think about what does a gaming company do apart from a lot of money? A lot of money. Okay, that's true. But you know what? I'm gonna skip the stuff that I don't understand. This is a gaming company, a really big one. Online gaming. This is all clear, right? I don't need to say anymore. Yeah, I can't even read it. This is the users table, which is basically the gamers, the players that they have in the system. Over there is the events table. There's a lot of information. There's a lot of information about each user in the system, right? Each player. The problem is exactly what you said. When they try to persist this into a relational model, it sucks. They have to write to 80 tables. Doesn't work. So they do blobs, right? On MySQL, and that's about it. Forget about it. I don't need to even deal with it. MySQL becomes a key value store. The only problem, slight problem, is what happens if you want to, during the game, for example, recommend, oh, these guys are playing right now next to you and you actually know them, so you should play with them. Or you should really consider doing this, or this offer is presented to you, etc. That data isn't available. You can't run a query on top of it, right? This is the flip side. So I don't know what's in there, but at least I don't worry about it. What's happening with our system, they actually came to talk to us because they wanted to get that insight into the data. But what they've learned is not only can they run queries that join users with a bunch of their attributes and a bunch of events and do either 0 or 1 joins, it doesn't matter how many tables are there, but they can also get a user object in a single request from a single point or write one in exactly the same way. So it's a really good example of where people have had to go, especially at those scales, and where I've been there, don't want to go there again. I want a database that actually works. No disrespect. I spoke today to the guy that, two guys from IBM, one built the first DB2, the one that was for the mainframe, and the other one that when they did UDB in the bad days of IBM in like the early 90s, he was the head of all DB2 development. No disrespect, but we were just discussing it. When you design a database, you design for the hardware and for the requirements at hand. In the 70s and the 90s, it wasn't the same. There weren't the same requirements. So, any more questions? Wow.
What's the interface of this? Are you writing SQL queries? Are there multiple ways to get in and out?
I'm out of here.
Nice. Actually, why don't we just jump straight to, oh wow, my voice sounds weird. Why don't we just jump straight to looking at what the actual interface is. Let me pull that up here. Make sure you can read it. That's a dexterity test. Okay. I can't do this backwards. That's not going to work. Oh, there we go. Okay. I can't do mirror displays. So, this is awesome. This is teamwork. So, first of all, the interface to us, the wire protocol that we use is Postgres. We use a Postgres driver to connect to Keyban. And what I wanted to show you actually in this demo was something very basic. So right now, we're looking at what we call the output mode of tabular output mode. So Ori was talking about the fact that we don't care what kind of data you get in the database, and we're trying to make it easier for you to use the database with whatever paradigm you prefer. So right now, what you're seeing is some really simple stuff. I'm selecting everything from a customer table. Basically, you see a tabular result set. Let me change this. I'm going to try to do it without typing if I can help it, because I'm a fat finger everything. We'll switch it to JSON format, and I'm going to run the same query. And I'll run it twice so that we can get it back up on the screen a little bit higher. So you can see the difference in the output. Now we're getting JSON output out of the database. I'm not selecting this out of a single data type. So it's not a blob that's actually just holding a JSON document. It's actually a set of logically relational tables that we're presenting to you in JSON format. To give you a better idea of what this actually could mean, we can also access the database like this. So RESTfully. So I can actually connect to my local machine on the most secure port in the whole world and access my schema just like this. So if I want to, I can actually get all of the data directly out of the database like this if I want to. And let me see if I can do something like that. So I can actually get several records out of the database if I want to. And then let me show you a little bit of an easier way to see this. So we've actually got a little bit of a demo here that'll show you how this works. Look at this window down below, and I'll scroll down so you can actually read it. So here you see a series of DDL statements and then DML statements down below. I'm going to create my database definition, and then I'm going to load some data into it. So anybody who's worked with a database before recognizes the SQL here. We'll execute it. We've got a nice little JRuby interface, and there we go. All the output of what we just ran into the database. Drop the tables, create the tables, insert the data. So then we'll go into another interface and show you how we can work with JSON. So new user, I'll add new user. I'll add Newt. We'll get Gingrich in here, and I'll make my pinchy face like that, and we'll add them. So then, if I want to look at this information, so now I'm loading JSON. I know that it's not really obvious from here, but the output is actually coming here at the bottom of the screen, and we're getting JSON in, and then we can actually query the database to see what I've added. So if I just go in and say, give me everything from the customers table, then let's do that. There's my new user. There's my Newt Gingrich. So I've added the JSON directly into the database. and I can query it back out if I want to using this interface, or I can do something a little bit more interesting. So let's say I didn't want to get an individual row. I want to get an entire object. Show me all of my customer data. Give me one document that shows me all of my customers. So we're a SQL database. We support ANSI 2003 standards, but we're going to extend it just slightly. So instead of select star, which every DBA in the world encourages developers to write, we're going to do select star star, which is twice as good. And when we run that, we actually get the entire object out. Now you can't really see what this is, so let me do a little bit of copy paste here. And I will pop this into JSON lint. So I'll paste that little string in there and validate it, and boom, we've got our customer record, we've got the order information, we've got the item information. And we can see that organized in a standard JSON document that I pulled directly out of the database. So does that help kind of illustrate a little bit more about what Ori was saying about how the database actually works? Let me show you guys, okay, it's getting a little weird. Let me show you guys how we actually organized it, but I appreciate it. How this actually, I'm not going to tell my wife that we just did that. So the way that we store this information in the database, the way that this actually works under the covers is with a structure called an HKey. So like you were saying before, we're actually going to be giving you the access to the information as though it were denormalized without actually exploding the data underneath. And there's got to be a way that we manage that information to make that possible. So the way that we do it is with an HKey, call it a hierarchical key, a horizontal key, or just an HKey. Doesn't really matter. It's kind of like how you pronounce the name of our company. But when you look at what we're actually doing, we're interleaving the data. And what we're doing here is very similar to a data warehousing optimization. If anybody's seen a cascading key, that's exactly what we've got. Now, why are we doing that? What does that allow us to actually achieve? First and foremost, when we interleave that data, as Ori was saying, think about shuffling a deck of cards as it did the opposite of what it actually does. So if you went to your Nirvana Vegas, where everybody wins every time, and they shuffle the deck of cards, and they're giving you runs. I'm organizing the data in order when I shuffle it. So now, I'm actually keeping track of every ancestor that I have when I hit my data row. So when I go to my item row, I know the provenance of where it came from. I know the customer and the order that it came from on every single row. I'm storing that information together on a data page. That lets me optimize my database in a much different way than I typically would. I'm not going to be doing what I always called defensive indexing. I got in trouble for talking about the kind of DBA I was before and the systems that I DBA'd, so let's just say it was a SQL solution. What we did was defensive indexing. How do you stop queries from having to do too much sorting and creating too many temporary structures when you join? I mean, too many temporary structures. But how do you minimize the impact of sorting? You create foreign key indexes. So when you actually go to run your joins, you have indexes that you can use to merge the data. In this case, we don't have to worry about that kind of thing because we've already pre-computed the joins. The data is already stored in its relationships. So what we're doing here with indexes now is we're creating the use cases for your objects. How do you use objects in your application? What are you trying to do? If you're getting a customer object out of the database, do you typically order it a certain way? If you get order information out, let's say from Amazon, for example, because customer order item, shopping cart, everybody can get their head around Amazon, right? So in Amazon, you're probably going to be looking at things in order date descending. So let's create an object over all of your customer order item data by order date descending. And then when you want to pull it out of the database, sure, when you're warming up the database, you're going to be using the disk. You're going to access the disk. But as soon as you've warmed it up, it's more efficient now because you're pulling a single index structure out and you're holding that up in memory. I don't have to merge it in memory like I typically would in a SQL database. So why do you denormalize? You denormalize so you don't have to join. It gives you the opportunity, if you do something called an indexed view, to create an index over what would be a denormalized structure without having the normalized structure. Have your cake and eat it too. It's great. But what we do here is better than that because we have an index now that we've got in the order that your object or your application wants to use it with the object. And we can pull that up into memory. We no longer have to merge the customer order and item indexes at runtime. We just keep pulling from that single representation of your object in memory. It's far more efficient. It lets us keep things resident in memory longer. And we actually are having a lot of fun at the IDF conference. Ori was just alluding to it. So we've been at this Intel Developers Forum this week. And we had a really great opportunity from Intel. They said, what would you do if you had a system that you could run a benchmark on that wouldn't be constrained by the normal things that you're constrained by in a benchmark? What are you typically constrained by? CPUs. We've got 80 logical threads on the machine. Memory. We've got a terabyte of memory. When we were throwing it out, we were supposed to be modeling a big data problem, and so they asked me, Mr. Product Manager, you go around waving your hands and talking about Web 2.0 all day long. So how do you define big data? I said, well, let's use a terabyte of data, but in order to show it off in a key bin, we're going to need a terabyte of RAM. Bite your lip. Oh, just one? So that was fun. So they gave us a machine, it's got a terabyte of RAM in it. Now what? Well, now we've got a disk problem. If I want to show both in-memory access and what happens when I have to pull data both from disk and from memory, then I need more than a terabyte of data loaded. So they gave us 4 terabyte of PCI SSDs. Sure, they got them laying around. Why not? They created 3 identical systems, one sitting in the trunk of the guy's car, one's in his house, and one happens to be at IDF. It's fun to work with Intel. So we run the benchmark, and it's amazing what we actually see, a 10 times performance improvement relative to ungrouped tables. When we look at a relational schema and a grouped schema, we can call ours a relational schema too, but we've grouped the information like Ori showed you. And all of a sudden, you realize what that does to unbound your application, because we're actually able to take advantage of the memory. Now, the cool thing is a knock-on from this, we're going to start working with Intel to find out what happens when you can actually use that amount of memory and start using persistent memory, so non-volatile memory. What happens if your system crashes and comes back up? If we can actually store everything that we've represented in memory and it's still there when the machine comes up without warm-up, then those possibilities are really, really cool. What else are they working on? Hot add memory. So now we can scale up a machine at runtime without having to restart. It's kind of challenging when you think about it. We're a Java-based database. The entire database is written in Java. The B tree's Java, the execution engine's Java, everything, the whole stack. So now you've got JVM issues, but that's a fun problem to try to solve when you're working with people like that, with hardware like that. So they're going to start hot adding memory to the machine, and they want to see us scale the memory utilization of the database in line with that. So constantly available. Now, why are we talking about all of these different things? The answer to big data is a tough one. What's the best solution that you use for a big data problem? You use relational databases. Well, Oracle will raise their hand and say, yes, you do. Absolutely, you do. Talk to our sales guy, though, first, and then come in, and we'll show you what you can do with your big data. So I'll give you some examples of ways where relational databases are challenged. I'm not here to bash relational databases, just like Ori's not here to bash relational databases. But some things are hard. So we talked to a company that's in healthcare. Now, healthcare has a few problems that people are familiar with. Electronic medical records, patient records, right? How complicated can a patient record be? What comes to bear with a patient record? You've got the person, he's got a physician, he's got healthcare providers, he's got insurance, there's documents, there's bills, there's all sorts of things that start to happen, and you get this big branch of everything that's related to that user. So when you want to pull a record, I mean, sure, you might be standing there and you're waiting for your turn, and you know, the person that's really bored looks up at your name, address, insurance, and they're slowly pulling all the data. But now imagine that you go into anaphylactic shock and they're taking you to the hospital and they're trying to figure out why you're foaming at the mouth and your eyes are rolled up in the back of your head. You'd like to think that they could access all of the relevant information to find out, can I give him this drug, or is it going to react negatively with something else that he's taking? Even though we're trying to save the person's life, let's make sure we can do it correctly. Now think about doing that at a massive scale. So in a hospital, in an ER, they've got to be able to access all of this information very, very quickly and concurrently. So that could be considered a big data problem. But let's talk about a different one that's a little bit more basic. It's mechanical. So we talked to a healthcare provider that has MRI machines. Those MRI machines have what we call in product manager world exhaust, right? It doesn't really mean anything, but they generate log files. So they've got all these log files that are coming out of the MRI machines, and they're in XML. So they've got between 2 and 3 million files generated every day. The files are between 200K and 5 meg each. They've got to be able to ingest that information, but they've also got to be able to parse it in real time and understand what's going on with those machines. Is the next customer that's going to, patient that's going to come in, they are effectively customers, and gets an MRI, going to have a working machine, or is it going to crap out in the middle of the scan? Because maybe the fan has been overheating, or the fan isn't even working. Maybe there's something else wrong with the machine. How would they know that? It's creating 3 million log files a day. You've got to be able to put it into a system and actually understand what's being generated in those files. What is it trying to tell you? The problem that they're trying to solve, and they're using DB2, which has been around forever, and they've got huge hardware, and they've got all the best consultants from IBM helping them. But how are they going to ingest the data, and what are they going to do with it? They can put it into an XML data type, but how many people have run XPath queries really performantly and scalably? How many people have thought about that kind of a problem, though? Because you think about it, there's databases like Postgres that are touting their new JSON data type, and they're all excited about it, but what does it actually mean? You're still letting the application do all the work. You don't know what's inside of your database. So when they try to model this problem and make sure that they're catching all the information, they're trying to ingest that 3 million record data. So they're actually using another SQL database that I won't mention because we're talking about MySQL here. But they put all the data inside of that database, and all they can really do, the best thing that they can do is process that XML file as it's coming in through .NET, so guess which database it is, and then they put it right back into the database as XML. So it's a one-shot deal. You want to process it again, pull the XML out, process it again, put it back in as XML. It's not very helpful. You can't report off of it. I mean, you could, but you're running MapReduce. You're letting Hadoop go off and do things for hours. It's not going to help you operationally do something. When a tech comes in and says, oh my God, your fan is out and this machine is so hot, how long has it been that way? Well, hang on. Let me run some MapReduce programs against my database and find out exactly how many log files have been generated since it started to overheat. It's not a realistic way to solve the problem. So what we're doing with a lot of these companies is trying to show them that we could ingest the JSON and actually put it into a relational structure logically. So now we've got metadata. You can understand what's inside of the database. You can figure out how to write a query against that data and actually understand whether or not that thing has been throwing a heat warning for a long time, or if the fan stopped working. Because we've got the tabular representation of that data, and you can write SQL against it. You can run reports. Now, that's a big data problem, and that's a big customer. We've got a lot more sort of closer to home, let's say, types of customers. So let's talk about something that everybody is familiar with, collaboration and social media. So that's easy, right? Everything is becoming social. GitHub is social. When Ori and I are here on the West Coast, because we're Bostonians and we're clueless when we come out here, Yelp is our best friend, right? Everything we do is walking up and down the street like this with our Yelp. Are we going to stop here and eat? Hang on, 2 stars. No, keep walking. Okay, great. So that is something that becomes a big data problem. Why is that a big data problem? Well, we went and talked to a gaming company because gaming becomes more and more social with network games. They're trying to get people, not necessarily to play the games at work, because that wouldn't be terribly responsible, although Facebook is making a killing doing just that, but they are leveraging the power of Facebook. They want to taunt you and have your friends taunt you and have you taunt your friends about all the things that you're going to do with that game as soon as you can get out of your boring job and go back home and play it. So you can get tokens while you're at work. You can challenge people to play certain things when they get home. So if you think about it, there's games like Rockstar that are becoming half Facebook, half network game on a console. So while you're at work, you get all of the coins and tokens and things that you need to get power-ups and more points and all the other things that you do so you don't have to grind away at the game. Some people are shaking their heads. This is some new terminology for me too. It's not the kind of thing that I'm used to, but I get the point. It's an understandable problem, right? You're telling somebody, I challenge you to play a game with me. And at home, I'm telling you that I'm going to beat you by this much. It's old school trash talk. But the way that they're doing it is through Facebook, through social media. Now, what happens with that is generating XML for them. They're storing it back in the database, and then they've got to be able to replay that while people are playing the game. How many coins did I amass during the day? What challenges do I have to face? Who am I actually being challenged by? But more interestingly, what's the graph of all the people that have played this game, that have challenged one another, that have won or lost and played again? So think about a Final Four tournament. The way this is growing is almost backwards. They're taking the winner first, the first person that makes the challenge, and then it's spider webbing out to all the different people that have been challenged, and all the people that have won, and all the people that have lost, and have played again, and have gone and bought more tokens, and come back in and challenged again. And they're having to represent all of this information in real time because the leaderboard is becoming something that's no longer a flat table. The leaderboard is now a graph of all the different people that have ever played that game, that have ever challenged you, all the times that you've ever played it and won or lost, and who you've won or lost by. So when they're trying to represent this information, think about writing those kinds of nested queries in SQL. Think about doing it through collaboration and social media app that we're showing here, which is a business-to-business collaboration tool. So in a business-to-business sense, think about Facebook if it were business data. You wouldn't be able to share an awful lot of information from your company, right? You can't just take documents from your company like you have in Google Docs and share it with the whole world. There's restrictions, and rightly so. So the problem that they had with this app that we're showing you here is when you try to have a group of people in your organization use something in social media, clearly the company that's allowing you to do that has to make certain guarantees about data security, about the way that they're going to let people interact with and share and see that data, right? So you've got a team of people from work and you've got a set of documents. Now, I want to be able to share one document with another person and collaborate on it. So think about consultant work. if you're not using Google Docs, if you're using something outside of Google, right? So I've got this document that I'm working on. It's the definition of my new product. It's the thing that is going to make my company take off. I've hired some of the best consultants in the business, right? I've got Erin sitting there. She's just chunking away at my database and making everything work super, super fast. But she can't do that with an app like this because they can't afford at runtime to run the queries in SQL that would join all the tables together to show the roles and the permissions for all the users while they're also trying to access the schema and just look at the individual documents and what they mean and what revisions there are of those documents. Oop, wrong way, hang on, there we go. So this is the query that has to be run with every screen interaction. It has to hit all of these different tables in the database just to understand what's the state of my item. My item might be a document. My item might be a picture. My item might be a video. It could be really anything that I want to collaborate on. Which application is it tied to? They let you create virtual applications inside of their application. What's the text? What's the file? Is it embedded? So all of these different things have to be accessed and analyzed. All the different facets of this item have to be analyzed at runtime. And then on top of that, they've got to layer on security. Time to interaction. Does anybody know, and I know this is again, outside of the normal realm of speech, but time to interaction, does anybody know what it is? For a web application, what's the tolerable time to interaction? Just throw out a number. Anybody? 250 milliseconds. There was a recent New York Times survey. I think they talked to people like me instead of actual people, so we have to come up with something, right? So 250 milliseconds, does anybody know physiologically what that translates into? What happens in 250 milliseconds in nature? An eye blink is actually slightly slower than that. That's how long you have to get data out of a database. Now, whether or not that's time to interaction with a page load, I think that's pretty irrelevant and not really realistic if you think about it. But if you think about the tolerance for actually doing a database round trip from your application, so client to database to client, 250 milliseconds actually isn't that short of a period of time. Think about how responsive your app has to be. Think about what PHP has to do before it renders a page. If you have a database query that's taking 2 seconds, think about how long your page load is. If I click a button and the database call takes 300 milliseconds, then my app is going to probably take about 3 seconds to the end user, maybe 2 if I'm lucky. It depends how light the page is. Depends if you start loading things kind of like the Facebook app does, where you have little areas of the screen that are going to start loading first, so at least you have a feeling that something's happening, right? So with an app like this, the only way that they were going to be able to take this app to more and more companies was having incredibly quick response time. But it was also in allowing them to share information between individual collaborators across permissions lines. And so they had to do something that everybody's been doing with relational databases for a long time, but that can be really painful. Now, if we think about other problems that have to do with social interaction, think about online dating, just because it's a really, really easy thing to get your head around, but also because people make huge, huge businesses out of online dating platforms. One of the companies that we're working with is the second largest internet property in Europe. They have 94 million users. They are second only to Facebook in Europe. They are a dating site. So what do you do in a dating site? I think I actually talked about this a little bit the last time I was here. But you're looking for people who are either like you or like the representation of you that you want to digitally represent online, right? So I'm 6 feet tall, I have blonde hair, and I have a very big chin, as far as you're concerned on the dating site, right? But I'm looking for other people with all sorts of other attributes like mine. Now, when you try to search all that information, essentially what you're doing is a faceted search. It's like searching for something on Amazon. It's the same kind of an idea, right? You're looking for on Amazon electronics. What kind of electronics? A computer. What kind of computer? I'm looking for a Macintosh. What kind of Macintosh? An Apple. What kind? A MacBook Pro. Okay, I'm drilling and drilling and drilling and drilling. And then you get to the point where you entered some criteria and you're not finding what you want. So you start backing back out of that, right? And then you're going to apply different facets and drill in again. So I'm looking for a blue MacBook, and for some reason I can't find one, so I'm going to drill back up a level and pick a different color. The challenge in doing that isn't just that I'm running different queries with different predication, but how many predicates do I actually have to apply in the database? So it gets worse when you think about online dating, when you think about that sort of a problem. Because how many things are you searching for? You've got height, you've got weight, you've got eye color, hair color, hobbies, religion. I mean, think of all the different facets of a person that you care about. Now, think about the way one of these sites actually works. The idea is that they actually want you to meet somebody. I mean, that's how these sites take off. If you look at the ads that come up for It's Just Lunch or Match.com, they've all got these ridiculous percentages they throw out there of how accurate their engine is so that they've made this many marriages happen and things. Do they work? Of course they work. We work with people that have gotten married that way, and it's fantastic. I think the percentages are a little ridiculous, but whatever. So when you're searching for the data, you want to find somebody, first of all, who's actively using the system. So that's a temporal problem. Then you want to find somebody who's geographically close. That's a spatial problem. Now you're going to add on top of that other things that you want to use to weight the response or the result set that you're going to get out of the database. So what else do I want? I want somebody who's been logged in recently. I want somebody who's geographically close. And I'm going to order those people in descending order, right? So the longer time you spent between logging in, the lower you're going to be ranked in the list. The farther away from somebody you are, the lower you're going to be ranked in that list. But now let's add on to it all of the other things that you're searching for. If somebody has brown hair and you're searching for a blonde-haired person, they might not even show up in the list, or maybe they will. It depends where you live. If you're in Wyoming or Iowa, you're looking for a blonde, you might get a redhead, and you're going to have to call it a day. That's fine, right? But if you're in a place like New York, now you've got a very different problem. If you're looking for a blonde, it's not going to help me really limit things very much. So start adding on other things. And now you start to understand just how complicated these ordering and weighting algorithms have to be. Because not only are they looking for what you're looking for and when you logged into the site and how geographically close you are, but they're taking care of the person on the other end of the relationship. What attributes are they looking for? Are they being matched in your profile? Now you've got a really interesting graph of all sorts of different parameters. If you've got to run joins and you've got to run recursive SQL to get that information, then that's a really challenging problem. If you've got a NoSQL solution, or if you've got everything stored in a JSON document in a blob, now you've got to leave it all up to the application. I know developers are really, really good at what they do, and I know there's a lot of tools to do really interesting things with applications. But I would love to see this problem solved purely by letting an application pull a whole bunch of documents out of a document collection and then do all of that work in the application and still show me a 250 millisecond response time to actually iterate through the data. Leave alone the rest of it. Or let's take that restriction off. Get me my answer and render me my page within 5 seconds. And then see how many users you actually convert in an online dating use case if you're taking 5 seconds. So it's a really interesting problem. And you might think that this is a trivial example of it, but it actually is something that is very, very real for a lot of people. Millions of people every day rely on these sites for a lot more than just, oh, you know, a little joke. That has never happened to me before. Sorry. So I've been talking an awful lot, and I haven't asked you guys any questions. Does anybody wonder about anything that I've put up here? Does anybody have any specific questions about anything that I've covered, or maybe anything that I've glossed over or not even mentioned? Go ahead. So the one thing I clearly haven't covered here is if you're trying to do aggregations and columnar searches, right? I've been talking a lot about row-based access and set-based problems. Do we have to know all the problems in advance? No. So a lot of the customers that we're actually starting to convert to Akebans are people that have looked for other solutions than relational databases, but as add-on solutions. They haven't gone whole hog into NoSQL worlds, or they haven't completely denormalized their database. But whenever anybody asks me who my competition is, my honest answer is workarounds. That's my primary competition. Because if people are looking at how they can make a relational database do what they need to do in this sort of a problem, what are they going to start doing? They're going to use memcached. Okay, this data is very dynamic. If you think about a temporal problem, caching isn't going to help you very much, especially if it's a mobile app. And online dating sites need to have mobile applications because that's the most relevant way that you're going to capture youthful people that are trying to meet each other, right? I've been married for a number of years. I don't remember what it's like to date. But in theory, when you're out there at a bar, you want to be able to text somebody and find them or look somebody up on your mobile device and actually have a match that way. So, okay. If I'm doing that, then I can't cache the information because the invalidation is going to be ridiculous. If I'm just 20 milliseconds, actually, is how often the mobile data is going to send location data back. So you can't cache that. That's not realistic. Okay, what's the next thing you do? Denormalize. Now we've got data explosion. Now, storage is cheap. Memory is cheap. But you can't actually pull everything up and keep it resident in memory if you've exploded your data, unless you have a friend in Intel that's just pouring on a terabyte of memory at a time. Otherwise, that's not a realistic way to solve the problem. So what else are you going to do? Stored procedures. Aaron will never work for you. If you use stored procedures, forget it. Done. So what else are you going to do? Now let's think about some of the other workarounds. People use things like Redis. Why would they use Redis? Because they know the questions that they're going to ask. Because if I have a faceted search, there's only so many facets I might support. I might not let you dynamically enter anything into a search box. I might just have a bunch of checkboxes that you can select. And that way, it's sort of like choose your own adventure, but not really. There's only so many answers you can come up with. People can come up with a logarithmic equation and figure out just how many different combinations there are. I can model a set of pre-calculated information, put that into a Redis set, and bam, I've got the answer for my scalability problem, and that'll work just fine until I want to extend the app, until somebody like me comes to the developer and says, hey, in order to compete, I need you to add this. And that's when I get the eye rolls from the developers, and they go, you have no idea what you're asking for. And I go, yeah, I do. It's just another little feature. And they go, no, it's actually a lot more than that. Well, why is it a lot more than that? Well, because I denormalized all my data in Redis, and I don't have that kind of fidelity anymore, and I can't. And I've got to code a whole bunch of stuff to make that happen. I'm not just writing a query. OK. So what else do people do instead of that? Well, they use FullText Engines a lot, not because they're actually doing full-text searches. They're not using it for that. They're using it for the incredibly powerful attribute lookup capabilities of a full-text search engine. So how are they doing that? They're taking the data, again, ETLing it into a full-text engine, sort of losing the fidelity, but basically creating a subset of what they had in the relational database. But they're letting you get at it really, really, really quickly. So I'm going back to my example now of that online dating site with the 94 million users. They went from MySQL to Clustrix. They went from Clustrix to using Sphinx. They went from Sphinx, and now they're evaluating Elasticsearch. They're trying to do something that you should be able to do in a relational database, but you can't do it with 94 million people. Because in their case, they're not actually pre-qualifying everything that you can ask. They have to, in order to keep a user base that big satisfied and to keep them on their system, they've got to keep pushing the envelope of what that thing is going to do. So now the recommendations become more powerful. So now the weighting has to become more complicated. They have to be able to use SQL. So what they've come to us for is to actually take 2 Akeban servers and replace 8 Sphinx machines. And we don't actually know for sure that we need both of them, but you don't want to run without high availability, and it really doesn't make sense not to have 2 servers just in case you have a peak for some reason. Like if people go, holy crap, it just got a lot faster, and all your users go back into your system and try to use it, you probably want to be able to load balance across a couple of machines. I'm not trying to brag, that's not the point. The point is this architecture actually works very, very well when you eliminate the overhead of the joins and you still let them work with the paradigms that they're used to. So we add spatial data. How do we do that? We're a startup. We've had a product out in the market now for just over 2 years. So how do we actually let people do spatial data? When you think about a lot of the databases that do that, they've got spatial types, they've got polygons and all these other shapes. They've got all these different functions that they add for distance and calculating things with latitude and longitude. If we've been focusing on creating a new database and working on common access problems, it's a really hard thing to think that we would have cracked geospatial too. Well, we've got data scientists in our organization. There's a guy named Jack Orenstein. He created something called the ZCurve Index. What that actually does is give you the most optimal way in a relational system to find basically points on a map. But we can do nearest neighbor searches, for example, which is exactly what these guys need to do with an index. It's just an index. We let you store latitude and longitude data in a decimal field in the database. So you lose a little bit of precision maybe because we don't have the world's greatest data type for that. But think about what you can actually do with it. Calculate your lat and long distance. And then find me the people that are the closest. But when you think about what these guys are doing, having to run that part of the equation in Sphinx, utilizing its geospatial capability, and then coming back to Clustrix, which is effectively MySQL, and then getting all of the other metadata, not only is it operationally difficult to maintain, but it's also hard for the application to do because it's got to go to different data sources, it's got to use different paradigms, and it's also got to be able to take the information, hope that Sphinx is going to give it the answer very, very, very quickly, and the Clustrix is then going to be able to take the IDs that basically Sphinx just gave back and actually hit the database with those IDs and get the answer back from the relational database very quickly. What we do is we take the index that we created that's a geospatial index. Then we take the other group indexes that we created over the regular relational metadata, if you want to call it metadata, and then we put those two together. So we can interleave the values in the indexes at runtime. So you've got your spatial data that's going to show you with ZCurve, and it's called a piano curve. You guys can look it up. It's actually, it's pretty cool. On Wikipedia, there's a huge write-up on it, and it's actually very nice. On our website, we've got some more information as well, and if anybody's interested, I'm more than happy to send you a lot of the documents we have in the wiki that we used to design the feature. But we let you get the geospatial data, calculate lat and long distance, calculate a radius, tell me how many users you want to get. So I only want to use a limit 30. Hey, guess what? You can write a SQL statement that says limit 30 at the end. You don't have to worry about getting 80 points out of Sphinx and then trying to apply those to your SQL database and then figure out how you should be ordering it and how many of the points you actually want to take. We just let you write a regular SQL query. and we'll get you the answers back because all the information's in the same system. There's no ETL involved, so there's no latency that you have to worry about. All that mobile data just gets updated directly in the transactional system. So there's optimizations that we have to maintain as much of this information in memory as possible. Some of the things that Ori was talking about are really beneficial in the architecture because logically there's a lot of things that we can do to show you that logical view of the schema where the data is actually just being appended so we can very, very quickly change that information and then slowly fold it back, sort of lazily as you're using the application. But it minimizes downtime and it lets you keep that dynamic nature of accessing the data. Now, I still haven't talked about rollups. So if you want to do aggregation queries, there's a paper that Ori wrote. It was called the orthogonal architecture. It talks about basically the patented innovation that HKey presents. Orthogonal is perpendicular, right? So we've got row-based optimizations, and then we have columnar optimizations. The columnar optimizations right now are being implemented basically as just indexes, indexes on whatever you're going to want to aggregate, and then in-memory representations thereof. So the goal that we're going to be working on towards the end of this year, and I have to give my product management answer, which is extremely vague, but it's by the end of this year, we are going to be trying to have just in-memory representations of the indexes. So now, if you have basically a row-based problem set, your customer-facing or client-facing tool is doing set-based operations. But then you've got people on the back end, like me, who are wanting to see how effective it is at runtime. So I want to be able to hit the database. Now, when I was a DBA, I got very used to saying no to people like me all the time. You can absolutely not touch the transactional system. I am not letting you touch my operational database because it's going to affect my end users. MVCC or not, what you're going to run against the database with Crystal Reports or whatever you think is your little benign client is going to kill the performance of my system. So what we're actually doing to enable that, and what we want to do with the in-memory indexes, is give you the ability to represent the indexes that you need to run those sorts of aggregations. So I can see how many customers have I converted, or how many people have viewed this page, or how many ads have been clicked on that I've been serving in a particular campaign, directly on the relational data with an in-memory representation of the index. So now, when that data is being inserted, updated, and deleted, I'm not paying the penalty for that. Because really, that's part of the harm, right? If you're going to create all of the reporting indexes on top of the database that has to have all of the set-based indexes on there too, then I'm going to be paying the penalty for maintaining those indexes when really my end-user client-facing application is never going to use it. So we're avoiding the problem and giving you an in-memory index. Now, what the other benefit of that, like I kind of just mentioned very briefly before, is as hardware moves to non-volatile memory, when you're actually able to persist information in memory on a chip and survive a machine restart, now all of a sudden we've got a warmed-up database already because it's persisted that index to the non-volatile memory, and as soon as the machine starts up and comes back online, that index is now resident again. So that's part of the way that we're trying to treat that problem. The last thing that I wanted to mention on that is something to do with flexible schemas. So a lot of people like NoSQL or are going to NoSQL solutions because of this idea of a schemaless architecture. And I don't think schemaless is really accurate or fair, but whatever. It's a flexible schema. And it doesn't require you to take the system offline when you're changing the definition of the data. So HKey is working, we have MVCC, right, for concurrency control with basic DML operations. But if you think about it, really what we want to do is extend that so that you can do things like alter table, add column, or just adding a table. So if you think about some of the people that would be interested in an online dating site, it's the people that serve up the ads that are served up on the online dating site. All along the top and the bottom and the sides of the application are the way that that company is paying its bills. And if they want to be able to serve up the correct ads on the system, then they need to take advantage of an awful lot of intelligence and a complex profile at runtime. So what they're going to have to do, though, from customer to customer is, let's say that I am the guy who is responsible for a campaign for ads that is being served up on a particular site. And I run my report during production hours, and I realize that I'm not converting customers. I might want to start A/B testing some things. So I'm going to want to add some other things to the campaign that I can capture to figure out why I'm not getting people to click on my ad. Typically, if I would do that in a relational schema, there's only two ways that I can do it. I either have to alter the database, which means I'm going to have to wait a long time, which means that as a business person, I'm going to be a pain in the developer's ass until it actually gets released into production. That's no fun. Or you're going to create a table that has a lot of sparse columns. So I'm going to have a loosely defined schema that's going to have, column A, B, C, D, and onwards, or 1, 2, 3, 4, and onwards. And some of those columns are going to be null almost all the time, and you're going to have just data in a few of them, depending on what the campaign might be. That's not a really good solution either. So what we're doing with the keybin is allowing you to logically change that schema in line with whatever the JSON document or XML document is that defines that campaign while the system's online. And then we'll just start funneling the data into it so that I can run my reports against that same data. But what else happens when you alter a schema? It's not just adding columns or adding tables. Now you've got to optimize it for SQL access, right? A relational schema has problems with joins, but once you add indexes, a lot of those things go away. NoSQL solutions have problems with accessing data that they have in their document collections, but if you add an index, a lot of those problems can go away, right? So you need the ability to optimize the access. You're trying to optimize for in-memory representations of your data. So as we modify that schema, while it's live, we also have to be able to generate the indexes that are going to support the access to that data and keep it fast. So we need the system to be able to realize things like cache misses, like when we do a full table scan, like in our case what we do, which is called a group scan or an ancestor lookup or something like that, where we're having to really traverse the entire group in order to get you an answer instead of leveraging an index. So we have to be able to create indexes at runtime. Now, everybody knows that if you try to do a lot of these operations during production hours, what's going to happen? If I have a table that I decide needs an index and I run an add index, right? I alter my table and I add an index, or I just do a create index on an existing table, then that's going to have to iterate through all the data in that table and create that index, and I'm going to be chunking through CPU like crazy while it's creating the index. And I'm going to be doing a lot of I/O while it's persisting all the information, and great. That is not going to help anybody in production. But if I can just take the information and keep it in memory, if I can pull that metadata out of the database and just keep an in-memory representation of the index, then yeah, I might see a little bit of a hit, maybe, because I am clearly going to be using resources. Nothing's free. But I'm not going to be hitting the disk so hard because I'm going to have to access all of that data. I might be able to actually create the index with a lot of the index data that I've already pulled up into memory, and then some of the extra data that I've just added. A keybin has the ability to use multiple indexes at runtime, right? So we can leverage several indexes on top of an existing table, so that if you're querying something, let's say, and I don't have a covering index for it, but I do have effectively a covering index when I merge multiple indexes, we can take advantage of that optimization, and we want to see how far we can carry that with other sorts of use cases at runtime. It's a long-winded answer, but I'm a long-winded person, I'm sorry. Does anybody else have any questions? Yeah?
Your index merging, that's not like MySQL's index merging. It's actual really merging.
It's actually really merging, and I don't know if you want to go really deep on the answer, but you can.
You go one slide ahead. Thank you. So, to give you a sense, this is the schema behind the, well, this is part of the schema behind the dating website. So you can see there's users and there's a bunch of things about them, like the options, the statuses, all the information you want to know about the user. So in the relational system, say you have a query that joins a bunch of them, you'll pick the table to start with. Use that index and basically join from there, right? What we can do is two things. The first one is we already have and understand the group, so we can create an index that belongs to columns from multiple tables within a group. So I can do an index on user.name, user.paidoptions.value. I can see the columns from there. So I can create an index on multiple columns within the group because I don't have to jump around to produce it, right? All the data is right there. So that's one way we extend indexing. The second one is, to your question, say each one of those tables has 3, 4, 5 indexes. Depending on your query, we'll use as many indexes as useful from this whole group. So I may use 2 indexes from the user table, 1 index from the paid options, 1 from the locations, and another one from a different place, and intersect them to find the right data set. So for example, say I have a query that says, give me all the users who are active right now, are in San Francisco right now. So that's from that table. Paid options is professional or whatever, and some other predicate. So the query looks like select all the users, join with a paid option, join with location, join with whatever, where all these predicates, right? We will take all the indexes that fit. So we'll take an index on user dot whatever the predicate is, locations, the index on paid options, and each one of them is basically telling us for this paid option or for this location, here is all the users that fit, right? Now we're looking for the intersection of all of those. right? So we'll do that across tables within a group.
Kind of what MySQL's
Yep.
index merging does?
Yeah, so what MySQL does, it's
Either an intersection or a union, depending on.
right, exactly. So there's two main differences. One is it's on a single table, right? It can't do it beyond a single table. So what we see a lot is we'll have a 15 or 30 table group, and we'll use any number of indexes from that group. The second thing that is different is that the ordering in MySQL, they have to be ordered in the same way to actually use them. We can use them in any ordering that they support. And we'll basically just use the part that is necessary. So we get to a lot of situations like this company where they do have 6- and 7-way joins to try and pinpoint the users that they're after, and we'll just use indexes to find out who those are.
So are you using B+ trees or?
Yep.
You are?
Different question. A special variant of B+ trees that we needed to make interleaving of data very, very efficient. So that's what our tree does, and I can expand on that.
When you're merging these, are you storing actual row level values, or are you just storing page level values to say these are on the same page, and then do
That's
if you have the page in memory, it's
that-
cheap.
That's a great question. Remember the HKeys that Ari showed before?
Yes.
So basically, if I have an index on, yeah, sorry. The question was, I'll rephrase it as what I understood and see if it makes sense. The question was, do you store pointers from the index to the page or to the specific value within the page? Does that make sense? Is that what you were asking?
It makes your index is much smaller if you can just store page level values, which gives you much faster values. Your data is all co-located anyway.
We actually store all of that data. So our HKeys, those keys are very, very compact. We'll store all of them. And the reason is, when I have an index on user location dot whatever, one of the columns here, it actually not only points to that row, it points to it within the context of the group, right? So the HKey will have both the user ID and the user location ID. So what that means is that now the index from here that has the same attributes can be intersected with it to find only the users that I'm after. So we'll hold all of that value for each of them.
How do you decide how big the domain for each part of the key is going to be? Like, you may have 100 users or you may have 1 million users. You have to have a number of different values.
I'll repeat the question. How do you decide how to represent the values of those keys? Because there could be 100 rows or 10 billion rows in. Long answer. Basically, we have what we call segmented keys, and you can basically compact each part of it and append the next part. And there's separators between them. That's the very simple answer. Think of it as dots, like in a DNS, right? 192.0. Exactly. So that's a good way to think about it, but they are very, very compact.
I implemented something similar in previous.
Life.
A warehouse application
Yeah.
needed.
It
Makes a lot of sense.
the basic design of the system that we did still out of academia, basically out of MIT. So we had to deal with a lot of those problems, and we wondered, do we want to keep the full hierarchy for each row? And we decided to do that. And it gives you a huge advantage because you never have to join to go back. You know exactly where you are in the path. If you want to get the order of an item, you don't have to ask anybody any other questions.
Do you have any performance numbers comparing your approach versus more traditional ORM?
We-
Like a bar chart or
We do. So we just did this crazy thing with Intel. It was like a 3-week scrum where nobody was asleep. And yeah, I can share that. I don't think I have them on the presentation, but I'll happily share them with you.
We'll actually be posting some of that to the site soon. So,
Okay.
yeah.
But the basic idea is almost trivial. If you want to get an object and it's in one place, that's a lot easier than joining it from multiple tables. So in a sense, it was kind of, really, that's what it's pretty obvious, right? But we ran it anyways, and you get, basically the more tables you have in that object, the better the grouped version is going to do. I mean, just very trivially. I think the more interesting stuff is when you start. So I think that stuff is amazing. We're working with ORMs to integrate those capabilities. But I think the really interesting parts are where you have those profiles of your users or your customers or whatever, and you want to start asking questions about them in real time. And there's a sweet spot there that is very hard to hit with different tools. When you have an 8-way join, you don't really usually think about that as a good candidate for an operational system. So I think there's a real sweet spot there, which is very interesting. So we've shown that as well. Please.
It seems like one of the problems that would be difficult with this would be when you want to access information from your top level records, say your user, say these are users, over a large number of them. Now you're looking at mini IOs over many pages because you stacked all this other unnecessary data in between. How do you guys handle optimizing that kind of a
You're completely right. The single table scan, both read and write, is the downside of the system. So we've solved it in the read side of things, and I already alluded to it a little bit. The one part of the system that you still pay that price is administration. So say you try to do to delete a table, right? It's much easier. So if I'm trying to delete this table in a relational system, I'll just drop the B tree. But we can't just drop the B tree, and that's where the whole adjust your metadata and let the system evolve over time. Something like that, right? It's not actually a vacuum, but a different approach. It's similar, right? It's the same kind of idea. Don't do it right now. Exactly. Yeah. Yeah.
I see the advantage of grouping these tables physically, but what if in this case user role, multiple users have the same user role? Is it replicated for each user, or is there like a foreign key kind of concept?
That's a really good question. I'll show you a schema and it'll give you a sense, I think. Remember this one? This schema? So the question was, just to repeat it, what happens if I have a many-to-many relationship? I'm going to say it in my words. And do you have redundancy? So we recommend not to have redundancy. You could if you wanted to. But what we recommend is when you have a many-to-many relationships like this table here, right, that connects jobs with users. So where should it go? Which part of, which group should it go with? What I've proven, which surprised me, is that it doesn't matter, which sounds kind of crazy, right? Really where it should go is where it is most frequently used. Think about these lines, these relationships as joins. How often do you use them? Do you use more this join or this join? Put it with that side, basically. That's the simple answer. It doesn't matter because most of the time we reduce the total number of joins that you would need to do in the system, this case from whatever, 25 to 1. So hyper-optimizing to the next level of completely reducing it wasn't as much of a priority. But if you wanted to, you could put it on both sides. You'll get some redundancy, which we're not encouraging, but you could.
Something that I've been trying to figure out, I'm sure there's a simple answer because I've listed. Say you're processing the Twitter fire news.
The Twitter?
Twitter fire news.
Yeah.
Every tweet that comes in,
Yeah.
every user,
Yeah.
every millisecond.
Yeah.
How does insert performance scale when you're jumping all over the place at different objects?
That's a good question. How many hours do you have? No, I'm joking.
Database scientist either, so.
Simple answer. It works really well when you have transactions on objects. For example, if you use an ORM, you'll be very used to this, right? Because then it's all localized. The whole transaction is localized. So we get a huge boost. The question that you're asking is, what happens if I have updates that are completely random all over the place? there's this approach here that will keep popping up, which is we write journals very aggressively. And I won't update the data in place until a later time. You won't know about it, right? From your perspective, the data is holistic and transactional and ACID. Exactly. So we just proved that each one of our, so journaling just writes file. Each journal file is a gigabyte, just to give you a sense, right? And we recommend to have at least 50 of them, which sounds like a lot. It's very, very efficient because I'm constantly writing sequentially, and then I'm just folding in groups of changes, folding the back end. If anybody knows the Google file system, similar approach. Welcome. Anything else? What's that? Any other questions? Any other questions? Yes.
So you mentioned earlier using MVCC.
Yes.
So are you keeping multiple versions of the record in the table then? Is that where you're going and cleaning out the old ones after a while, where there's no open transactions?
Yes. In a very specific way, we keep the changes, so to speak, but yes.
And do you try to localize the rights so they end up on the same page, or you just don't care at this point for the new inserts and the updates?
Oh, we always do. So that relates to your question.
Exactly.
We'll journal the changes sequentially to the journal file very, very quickly, and don't bother with it for a while. Then we'll take a whole bunch of changes that go to a single location, to one of our objects, and fold them in together. In fact, we'll take bigger chunks and fold them in together. So, to your question, very much so. So we're trying to do, consider also, we're working with disks right now, so sequential is going to work very well. Think about SSDs. Updating place is the most efficient operation. It's not what you really want to do a lot of, but you have to do it at some point, right? So this is exactly that kind of approach. Write journals very, very aggressively and then merge a whole bunch of changes back into the tree.
But do you actually replace the records at that point, or are you still writing a new version and discarding the old one later?
Both. Yeah. So I mean, I can walk a lot deeper than that, but probably you'd hate me by the end of it. So, but it's a very good question. Yeah.
So I think you've only talked about running on a single server. Do you have like a distributed story?
Yep, we do. Do you want me to tell it to you? So the question was, do you have a distributed story? So one of the things we're looking with, and actually Intel is a part of it, is a backbone that is an object store through which we can share the objects that we deal with. And we will be releasing it pretty soon. So it's not what we sell right now. Right now our focus is single node or multi-node but replicated operational systems. And we sit alongside and solve especially those kinds of problems where you have either very complex objects and you just can't deal with them, or you have queries on top of them that need to be resolved in real time. Just because there was a sweet spot, so it was a great way to build the architecture. The next step is going to be, okay, with an object backend, so to speak, and our objects are usually around 64 kilobytes is our sweet spot. Now we can start sharing that across a backbone. You can basically start machines on top of the same backplane. So, again, I can give you a lot more information. Yep. Great question. We join them using joins that can be of different types. Pretty much what you would expect. So that join over there, literally the one in the middle, that is literally one that we're going to execute if we need to. We did a lot of work on costing, maybe too much, because most of the queries, even if they're like 10-way joins, get reduced to a single join. So how many options do you really have, right, in terms of join ordering, etc.? But we have done a lot of work on it. In fact, some of the work also translates to internally within a group. You don't have to join, but you still have to get the data. So we optimize the traversal within the group. So that there is cost-based optimizations within the optimizer to do that. I assume that's what you meant. Okay.
Is
Yes.
there limits on the join? The size of the object?
No. We'll probably reach it one day, though. It's out there. You know, at some point I said, whatever. If it's over 1,000 tables.
Like the dating sites store their images in there too, or they keep that off in a separate image store?
I'd prefer that they don't. You know, there's a whole bunch of immutable object stores, starting with HDFS and going forward, and I think that's the right solution for pictures. The metadata about the picture, I have different opinions there. Interesting? No? Any other comments? Cool. He's happy. Ready?